Hello students, welcome to this new module. In this module, we are going to discuss particle in a box. So let me illustrate what I mean by particle in a box. So suppose a particle is moving inside a box of side L, and this is a cubic box, and the motion of the particle is along the y-axis, and the walls of these particles are so rigid that this particle cannot penetrate. Okay, so as the particle is moving along x-axis, the whole problem can be simplified as follow, that the whole thing can be written as a particle inside this infinite box. Why I'm saying infinite box? Because the walls of this box is so rigid that particle cannot penetrate or cannot go out. So we can say that the potential at these two boundaries, x is equal to 0 and x is equal to L, potential is infinite, and inside the box the potential is 0, so the particle can move freely inside the box, and as the motion is along the y-axis, so we have just reduced the cubical box into one-dimensional infinite potential box. Okay, so if you want to see how the potential varies in spatial regime, we can write this, that potential V of x is 0 in between 0 and L, and infinite when x is smaller than 0 and when x is greater than L. Okay, so now the particle is free to move inside the box. However, at the boundaries, these are the boundaries, particle experiences a strong force and the potential is infinite, or you could see that the boundaries are very rigid. Okay, so now we want to understand the motion of this particle quantum mechanically. What it means that we would like to solve Schrodinger equation for this given potential with these boundary conditions. Okay, so let's divide the whole potential problem into two regimes. Regime 1 in which the potential is 0, and regime 2 in which the potential is infinite. Okay, so now in regime 2, as the potential is infinite, so what it means that there is no probability, there is no chance that particle can come out from these rigid boundaries. Okay, the potential is infinite, so we could see that the wave function is 0 when x is smaller than 0 and when x is larger than greater than L. Now in regime 1 we can write down the Schrodinger equation. Regime 1 is between 0 and L. Okay, so the Schrodinger equation is written as minus h cross square over 2m d2 phi x over dx2, as the potential is 0, so the v plus v time phi of x term will be 0, and then on the right hand side we have e times phi of x. Now we can rearrange the whole term and we can rewrite the whole equation in this following fashion. So d2 phi over dx2 plus 2me over h cross square phi x is equal to 0. So now we have set right hand side of the area. So let's try to solve this equation. So let me write this equation in this regime 1. So this is the equation that we have written, and now to just simplify the whole thing, what I'm going to do, I'm going to just assume a general solution of this equation of this following form, which is as phi of x is equal to a times sine kx plus b times cos kx, where k is your square root of 2me over h cross square. So this part I have assumed as a k square. Okay, so once we have written the general solution of this double differential Schrodinger equation for particle in a rigid box, now the only problem left to us is to find what are these constant a and b. Okay, so how we are going to find constant a and b? To find the constant a and b, we have to use the known properties of the wave function, what kind of wave function we are going to accept. Okay, so we have learned that the wave function must be continuous at the boundaries. What it means that the wave function at x is equal to 0 and x is equal to L must be 0, because the other side of the rigid box phi of x is 0, so at the boundary the wave function is supposed to be 0. So let's apply these two conditions. Okay, So we know that the wave function is 0 here, wave function is 0 here. So at these two boundaries, x is equal to L and x is equal to 0, the wave function must be continuous. It means that the wave function must be 0. Okay, so once we apply these two conditions, so once we apply, let's say x is equal to 0, what we are going to get? We are going to get a times sine k times 0 plus b times cosine k of 0. Okay, so of course sine k of 0 is 0, but b times cosine k of 0 is 1. So what we are going to get? B is equal to 0. Okay, that is the first condition we have got it. Now when we apply x at x is equal to L, okay, then in this case we will get this term automatically drops out 0. So then a times sine kl is 0. So then a cannot be 0, otherwise b is 0, a is 0, so the whole wave function is 0. We know that the whole wave function cannot be 0. So it means that the argument of sine must be n pi, then this term supposed to be 0. So if sine k of L is 0, then a times sine k of L is 0. Okay, so the kl must fulfill these conditions, that kl is equal to n pi, where n is 1, 2, 3, any positive integer value. Okay, once we have got this condition, then we can put this value and we can obtain the wave function as but before that we have to get the wave function. Let's substitute the value of kl. So k is equal to square root of 2me over h cross, that we have seen in the previous slide. And now once I substitute this value of k, that n pi over L, and in this way I can write down my energy as a n square pi square h cross square over 2ml square. Now you see a very interesting relation of the energy for a particle in a rigid box, that this energy is dependent on n, where n goes from 1 to 3. So n is a quantized in nature, so the energy is quantized in nature. Okay, and this expression is valid for n is greater than or equal to 1, as I have said it. Okay, so the energy is quantized. This is a new observation that you have seen, unlike in the previous case when particle was free, and in that case your energy was h cross square k square over 2m, and the energy was continuous, it was not quantized. But here the energy is quantized, and the consequence of this quantization of energy is coming because your particle is confined inside a box in which the particle is moving. Okay, so what about phi of x? So we have written my phi of x is a times sine, and now I have replaced the value of k by n pi over L times x, and the b part is 0. Okay, now we know that from the previous slide that kl is equal to n pi. Okay, now to find the value of this a, which we have called as a normalization constant, you will see in future, what we have to do, we have to integrate the phi of x square over entire space, and this value is supposed to be 1. This is the condition imposed by a wave function which is normalizable. Okay, so let's substitute this value. So our limit goes from 0 to L, where the particle is non-zero, modulus of phi square dx. Now phi x is this one, so what we will get, a square sine square n pi over lx square. That's what we have to work, and right hand side is always 1. Okay, now you can use the trigonometry relation to perform this small integral, and you can determine what is the value of a. Okay, so then you will see that your modulus of a square will come out to be 2 over L. It means that your a is 2 square root of 2 over L, and as there will be a plus minus sign, so to compensate this plus minus sign, we have introduced a phase e to the power I theta. Okay, in general the phase is very important. This is a very important quantity for a wave function, but for this particular example, particle in a rigid box, and to make the physics simple, we will consider that your a is a real quantity, and we will ignore this page in this particular example. Okay, so now we have obtained a is equal to square root of 2 over L. So in this case, now my phi n can be written as square root of 2 over L sine of n pi over L x, as your wave function is dependent on this quantity n, which is n is an integer, positive integer quantity. So now I have introduced a subscript in your wave function, phi n of x. Okay, so for a given n, I will get one particular kind of wave function. Okay, so now we have obtained the wave function and we have also obtained the a value by using the normalization condition. Okay, so now this is a summary that your phi n of x is square root of 2 over L sine n pi over L x, where x ranges from 0 to L and where your wave function is 0, and the corresponding energy of this wave function En is equal to n square pi square over h cross square over 2ml square, where n is 1, 2, 3, so on. Okay, therefore we can write by using these two obtained value that h times phi n of x is equal to En times phi n of x, and this is your eigenvalue equation, where En is an eigenvalue corresponding to this eigenfunction Hn, or wave function Hn. Where En is an eigenvalue corresponding to this wave function phi n, or eigenfunction phi n. Okay, now this is the first exercise that you have to do. Now once you have obtained the expression for phi n of x, then it is easy to compute the uncertainty in x and the uncertainty in px, and if you take the product of these two, then you can show that for a particle inside a rigid box, this delta x delta px is equal to h cross times square root of n square pi square minus 6 over 12. Okay, this result is very different what you have seen in the case of particle as a free, where your delta p of x is 0 and delta x is infinite. Here the product of these two quantities is finite, and moreover it is an independent quantity. So this is the exercise that you have to do. Let's move further. So one of the very important use of this simple model that particle is moving inside a rigid box is to explain different kind of colors of quantum dots. Okay, so what are the quantum dots? A nanoscale semiconductor arrangement is called quantum dots. Okay, and they exhibit size dependent colors. Okay, so you have seen that your energy for a particle in a box is written as in this following fashion, where En is inversely proportional to 1 over L square, where L is the size of quantum dot in this particular case. Okay, and as you can see that this is a experimental measure data for quantum dots. Okay, and you can see that the size is increasing from 2.3 nanometer to 5.5 nanometer. As the size increases, the color is also changing. So now you can say, or you can look that if you take the energy difference between the two energy levels, that means E2 minus E1, okay, then it comes out that this is a constant 3 pi square h cross square 2m, okay, and then the energy difference goes 1 over L square. Okay, so the size increases when emission shifts to the red side. Okay, so now we have seen the wave function and the total energy, that is phi n of x is this. Okay, and En is this. Okay, now let's write wave function and the corresponding energy for different energy levels. So for the energy level 1, your wave function will be square root of 2 over L sine pi over L times x, and En will be pi square h cross square over 2ml square, because n is 1. Now if you take the pi 2, then here you will get 2 because n is 2, and here because it goes n square, so you will get 4. Then for the third wave function, this is going to be 3, this is going to be 9. Okay, so now how these stationary states wave function looks like. So let's plot these wave functions. So the first wave function phi 1 is sine pi over L times x. Okay, so you can see that this wave function is 0 at the boundaries, means when L is your 0, or let's say when x is your 0 and x is L, then this is your phi 1x. Okay, and the corresponding energy is your E1. The second wave function, or the wave function corresponding to the second state E2 has one node in between, so it crosses the 0 at the center, and the third wave function crosses the 0 at 2 points, and you know the wave function must be 0 at the boundary. That is the condition that we have imposed when we have obtained the value of A and B. Okay. Now let's look furthermore. So here you have noticed that your energy is proportional to n square. Okay, directly proportional to n square. Now phi n of x, your wave functions are alternatively odd or even with respect to the center of the box. So that is easy to see that which function is even, which function is odd. Okay, what it mean that if you replace x by minus x, your wave function does not change the sign, and these kind of wave functions are your, let's say, the even function, and they are the n is equal to 1, 3, 5 with the odd n values, whereas your wave function get minus sign, so these are the odd wave functions, and n is equal to 2, 4, 6 means even values of n, your wave functions are even. Now the third property that you have noticed from the energy and the wave function, as n increases, okay, so you can see that 1, 2, 3, so we are increasing the value of n, the number of nodes or the zero crossing are increases. Okay, so these are the three important observations for the wave function and the corresponding energies for a particle moving in a rigid box, and these are very new features that you have seen, unlike what you have seen for a particle which is a free to move in a space. Okay, now let's how the energy looks like. Okay, so this is the expression for energy. Now we have seen that your energy is quantized because it changes with value of n, and it cannot have any random value. It can have only a certain values of n, where n goes from 1 to 3. So here you can see that this is your E1, this is your E2, this is your E3, this is E4, and if you express your E2 in terms of E1, then E2 is equal to 4 times E1, E3 is 9 times E1, and E4 is 16 times E1. This is just a consequence that your En is proportional to n square. And now the lowest energy, E1, is pi square h cross E square over 2 ml square, once you substitute n is equal to 1, which is non-zero. However, if you feel that the if you think in terms of the classically, your ground state energy is supposed to be the 0, or the lowest energy is supposed to be 0. A classical particle can assume any value of energy starting from 0 to any finite value, and this is a contradiction of your classical thinking. So this is a signature. E1 is non-zero, is a signature of your quantum physics, and the quantum particle possesses 0-point energy. This is the similar results what you have seen for a particle moving in a harmonic potential or harmonic oscillator, where your 0-point energy is half times h nu. Okay, so in that case also you have a 0-point energy. And similar observation you have seen that particle inside a rigid box can have also a 0 energy, which is non-zero. Okay, so now another thing that you could look how the probability density looks like. So what is the probability density? So probability density is the modulus square of your wave function. So if you plot, let's say, the phi 1 of x square, then it will be 2 over L sine square pi over Lx. So that is your probability density for the first state. This is the probability density of your second state, and this is the probability density of your third state. So this is the way that the probability density looks like. Okay, now there is another important concept that you have seen during the discussion of the Schrodinger equation, that your stationary states or the wave function must be mutual orthonormal. What I mean by this, so if you take, let's say, the two wave functions phi m and phi n, and if you take the product of the phi m star phi n, and if you integrate over space, you will get delta of mn, and this delta of mn is known as a Kronecker delta, and this is non-zero when both the indices are same, means delta of mn is 1 when m is equal to n, otherwise it is 0. When m is not equal to n, then this quantity is 0. So let's check whether this condition is fulfilled by the wave function for a particle inside a rigid box. Okay, so our integration limit is always 0 to n phi m star phi n dx. Okay, this is our wave function. You know that square root of 2 over l sine n pi over l times x. Okay, so this 2 square root of 2l will get 2 over l. Now the integration limit goes from 0 to l. The first term will be sine m pi over l times x, and this wave function is real in nature, so star will make no effect on this wave function, and phi n of x will be sine n pi divided by L over x dx. Now this you could think as a sine A times sine B over dx. Now you can use the trigonometry relation. So what you are supposed to get? You are supposed to get cosine A minus B minus cosine A plus B. So this is using the trigonometry relation that you have got it. And now you know what is the integral of cosine function. Okay, so it's easy to see that this term will go to 0 when m is not equal to n, and this term will be 1 when m is equal to n. So what we have concluded that the wave functions for a particle in a box of this kind fulfills the orthonormality relation. Okay, now let's see what when we apply this Hamiltonian on our wave function, what we are going to get. Okay, so our Hamiltonian generally is written as a kinetic energy term plus potential energy. Okay, so and the wave function, as we have seen several times, this is the wave function. Okay, so let's write kinetic energy. So minus h cross square of 2m d2 over dx2. Okay, so this is the kinetic energy operator, and the potential is written as in this following form, and wave function we have written. Okay, now the potential is 0 inside the box, so this term will be 0. Okay, so the only thing is left is this term, and this term when it operates on this quantity, what we are going to get? Let's do it as follow. So when you apply this one, you can see that this will operate 2 times to the sine function. This is a constant, so this can be taken out. Okay, and when it operates, it will give you back the sine function with lot of prefactors, and if you collect all the prefactors with this prefactor, then you will see that it will be n square pi square h cross square over 2ml square times this remains as it is. So then we can see that your when h is operates on phi n of x is equal to en times phi n of x, and then we can say that this wave function is an eigenfunction of this Hamiltonian. This we have already said it, but here what I have shown is mathematically proven that this equation indeed hold. Okay, and then we can say that these states are stationary states which are of definite energy of En. Okay, so these are the stationary states of definite energy. Okay, so as I said that these phi n's are now known as eigenstates of this operator H, and En are known as eigenvalue. Now let's see when your momentum operator operates on your wave function. Okay, so this is your momentum operator minus I h cross times d over dx. When it operates on this one, you know that it will give you minus I h cross, and d over dx will give you n pi over l, and this will convert into cosine. So square root of 2 over l cosine n pi over l times x. Okay, this is not equal to phi n of x, right? Because phi n of x is this one, so this cannot be converted by any means by phi n of x. This means that this function phi n of x is not an eigenfunction of your momentum operator, and this is a very different results what you have seen in the case of particle is free. Okay, thus the stationary states are not eigenstates of the momentum operator. In other words, phi n of x are not states of definite momentum. Okay, so then we can ask the following question: what is the momentum of the particle in the stationary states? Okay, but before we answer this question, these are the two questions that you have to answer. The first question is that determine the energy levels of a particle in a box using de Broglie equation, not the one that we have done it here, but using a much simplified approach using the de Broglie equation, means that lambda is your h over p, okay, or h over mb. The other question that you have to answer is show that 0 point energy, that is E1 is the consequence of the uncertainty principle. Okay, so these are the two questions that you have to answer. Okay, now let's talk about momentum for phi n of x. So when we talk about what is the momentum of associated with the wave function, it is uh, meaningful to talk about either average momentum or the expectation value of the momentum. We have seen how to estimate the momentum value of your operator. Now you have noticed that when we are defining here the expectation value of this operator, we have removed a divided term, that is integral of phi n star phi n dx, what you have seen in the case of free particle. The reason is simple, because here your wave function is normalized, so we don't need to normalize the whole value again. Okay, unlike for a particle in free particle where the wave function was not normalizable. That's why every time we have to divide the any expectation value of any operator for a free particle wave function. Okay, so let's estimate the expectation value of a momentum operator. So this is your momentum operator. Now we know what are the values of these two quantities. So once we substitute these two values, sine n pi over Lx, sine n pi over Lx, both the places. Now this is your momentum operator. I can take minus I h cross outside, and the normalization of this and this will give you 2 over L. So now once I will operate, what I will get n pi over L. So I have got n pi over L. 2 over L is there, minus is cross is there. So what I have got, sine n pi over Lx, cos n pi over Lx. Then you can see that the integral of this quantity turns out to be 0. So then what it means, that the expectation value of momentum is 0. Okay, this is also true for expectation value of your Hamiltonian, and the value is here. Okay, but here we have to additionally see that the variance or the uncertainty in your Hamiltonian is also 0, because you can verify this small one line exercise by yourself. But what is the meaning of this statement? That the stationary states have a definite energy and there is no uncertainty associated with En. Okay, thus the stationary states of one-dimensional box for a time-dependent wave function can be written as phi n of x and t is phi n of x times e to the power minus I E n t over h cross. That is the general expression for any time dependent wave function, which is written as a product of the time independent wave function times energy dependent phase. So this is your time independent wave function, and here I have substituted the value of energy. So now the time dependent phase will read as e to the power minus I n square pi square h cross square over 2m L square times t over h cross. Okay, so now let's recall what we have seen in the case of time dependent Schrodinger equation. In the case of time dependent Schrodinger equation, if we want to write any general wave function psi n of x and t, it can be written as a summation over n, where n goes from 1 to infinite. This is a coefficient Cn, and now we can take the linear superposition of several phi n, okay, and that will give psi n. Okay, and now we have to take a time dependent phase, so we have taken the time dependent phase as e to the power minus I E n t over h cross. Okay, so this is our general solution of time dependent wave function. Okay, where Cn are the complex coefficients. Okay, for an infinite potential box, we can have this is your phi n of x. We are using the same color, and this is your energy that we have seen. So this is any general wave function which is a time dependent in nature, which is a linear superposition of several time independent wave function weighted by this coefficient Cn, which is in general complex in nature, and the time dependent phase. Okay, now the question is that how to determine this complex coefficients which determine what is the weightage of different combinations. Okay, so this we will see in the second part of this lecture, which you will see in a moment.